Good morning, student. Today we are going to discuss the topic homogeneous hydrogenation. In our previous classes, we have already discussed the heterogeneous hydrogenation of hydrocarbons or alkenes. Today we are going to dealing with the homogeneous hydrogenation of alkenes or hydrocarbon. From the word itself, the homogeneous hydrogenation is explaining that this hydrogenation is carrying out in a homogeneous nature, that is, here the catalyst and substrate and reagent molecules are existing in a homogeneous nature. That is, there is a homogeneity is existing between the substrate molecule and the catalyst. And the most commonly used catalyst in the homogeneous hydrogenation is Wilkinson catalyst. Wilkinson catalyst. And Wilkinson's catalyst is existing in triphenyl phosphine rhodium chloride, and generally this catalyst is red in color, and this triphenyl phosphine rhodium chloride is used as the homogeneous catalyst in the hydrogenation process. And this catalyst, when it is red in color, and generally it is soluble in methanol and ethanol. Okay. And when during the hydrogenation process, when hydrogen molecule is added to this triphenyl phosphine oxide, it will turns its color from red to yellow color. And the schematic representation or different stepwise representation of the process of homogeneous hydrogenation is explained. That is, here we are starting with our triphenyl phosphine rhodium chloride, which is used as the catalyst here. Triphenyl phosphine rhodium chloride. PPH3 thrice RHCl. And on the addition of hydrogen to this catalyst, generally it is red in color. On the addition of hydrogen to this catalyst, here is an oxidative addition is taking place. An oxidative addition is taking place in this process. That is, the structure of our catalyst will turn to a hexa-coordinated compound. Hydrogen is added here and chlorine is keeping as such. Here generally we said that here is an oxidative addition is taking place. Oxidative addition is taking place. Okay. Then to this adduct, that is, it is oxidatively added complex, and from this complex a large molecule or a bulky molecule, that is, here is this triphenyl phosphine molecules are the bulky molecule in this complex, and from this complex one of the triphenyl phosphine molecule is leave from this compound. It leads to the formation of the structure. That is, one of the triphenyl phosphine molecule is leaving from this compound, and the structure is like this. That is, here is the structure may be called as trigonal bipyramidal shape. So this is the next shape of the compound. That is, here in the triphenyl phosphine, one of the molecule of triphenyl phosphine is left from this oxidatively added complex structure and result the molecule like this. Okay. After the dissociation of this triphenyl phosphine oxide, there is a vacant spaces existing in this metal to attack our alkene molecule to this complex. So, our alkene molecule or our hydrocarbon, unsaturated hydrocarbon, is coordinatively added to this molecule in this stage. Okay. So, the structure may be like this. Our coordinatively added molecule may be represented as here. This is our alkene molecule, and during the coordinatively addition, the structure of new molecule may be represented as the rhodium molecule, chlorine, hydrogen, and here the coordinatively added hydrocarbon. It is the coordinatively added hydrocarbon. And from this coordinatively added hydrocarbon is showing a type of rearrangement to form an RHC bond. That is, here this CC bond is shifting, resulting a metal carbon bond is formed. And in order to form this metal carbon bond, this CC double bond is shifted to either of this carbon atom, and here then a CC bond is formed, and the rest of the carbon atom is occupied by one of this hydrogen molecule. Thus, the structure may be represented as like this. A RHC, that is rhodium, and the bond is forming between rhodium and carbon, and next carbon atom is occupied by a hydrogen atom from this complex. Suppose this is the position where hydrogen atom is attached, and rest of the molecules are keeping as such. Okay. Then the next step is the reductive elimination of this compound. Our coordinatively added alkene is now turns to its alkane form or its saturated form, and the next step is the reductive elimination of this complex or this compound from this whole complex. That is, it can be represented as, during the reductively elimination process, the bond between rhodium and carbon atom is shifted to rhodium atom, and it results an abstraction of this hydrogen to this carbon atom. Thus, here is we have already said that the reductive elimination is taking place in this step. Reductive elimination. And reductive elimination leads to the regeneration of the catalyst and expel of the product of that is this the added alkene is reduced to corresponding alkane form. That is, it can be represented as like this. Twice RHCl. Here the reductive elimination is taking place, uh, and it results the formation of this alkene. And from this it is clear that the addition of this alkene is generally a syn addition, is addition of hydrogen to this alkene is a syn addition. Syn addition is taking place, or the product formed like in syn addition. Okay, this is the basic mechanism or basic schematic representation of homogeneous hydrogenation process. That is, here since this syn addition is taking place, the both of the hydrogen atoms are added to this alkene from same side. Or, hence, this type of the product is formed. Then let us discuss some more example for this homogeneous hydrogenation. Okay, yes, one of the most important example is, suppose we are taking a molecule of succinic acid, in molecule of malic acid. Structure of malic acid is like this, and during the deuteration process of this succinic acid in presence of our catalyst triphenyl phosphine oxide, triphenyl phosphine rhodium chloride. Triphenyl phosphine rhodium chloride, and it results as product, that is succinic acid is formed, and both the deuterium are added in same position to form this succinic acid, or we can say that the product is a meso product, or meso deuterated succinic acid. Mesodideutyrated succinic acid is formed. At the same time, if we are taking fumaric acid, this is malic acid. The fumaric acid may be represented like this. On deuteration process in presence of the above catalyst, triphenyl phosphine rhodium chloride is used as the catalyst. Here we will get a DL mixture of this product. DL mixture of the product is obtained, plus another type of enantiomer is obtained. So this is one of the example. So in all these cases the syn addition is taking place. And another type of example is, generally this type of catalyst, that is triphenyl phosphine rhodium chloride, is used for the hydrogenation process of alkenes, and normally these are used in the case of non-conjugated alkenes. Non-conjugated alkenes are normally reduced by this type of catalyst. And generally, if we are with a compound having a functional group of oxo, nitro, cyano type functional group, cyano or halo, and azo type functional groups are there. If we are with a compound having these type of functional group, they are not reduced by this type of catalyst. And if we are compound with this type of functional group and an alkane, this type of functional group and an unsaturation is there, in such compound that unsaturated CC unsaturation is generally reduced by this our catalyst. One of the example is, suppose our compound is NO2 functional group is here. During the hydrogenation process, in presence of triphenylphosphine, rhodium chloride as catalyst, in presence of benzene, this CC double bond is getting reduced and not reduced this NO2 functional group, or not considering this NO2 group. CH2, 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 NO2. And another type of example is, suppose we are with a compound having functional group. This is a cyano group is the presence of the catalyst triphenylphosphine, rhodium chloride and benzene. Only this double bond is reduced and not considering the CN group. Okay. So these are some of the example. One more example is, suppose we are with a compound having a carbonyl functional group. In presence of the catalyst, what is happening here is that only this double bond is getting reduced, because this double bond is getting reduced because this CC double bond is in existing in a saturation with, or in conjugation with, this carbonyl functional group, or so it is not reduced in presence of this type of catalyst. So the product will be like this. This is the product. Okay. Then one more important factor is, if we are with a alkene or unsaturated compound, unsaturated hydrocarbon having mono and or di substituted double bond. In presence of this mono and di substituted double bond, generally mono and di substituted double bonds are getting reduced as compared with tri and tetra substituted double bond. That is, one of the example is, suppose this is the example. During hydrogenation process, in presence of benzene, this is our alkene. Here we can see that two CC functional CC groups are there. CC double bonded groups are there. That is, here according to this position, here this CC substitution is this CC compound is substituted with double bonded compound is substituted with only one substitution is there, but at here at this unsaturated position there is 3 substitution are there. Comparing these two, we can say that less substituted double bond is getting reduced. That is, here is this is mono substituted and this is tri substituted. Hence, compared with this tri substituted compound, this mono substituted compound is getting reduced. Mono substituted compound getting reduced and keeping tri substituted as such. So this is the product. Another example is this one. In presence of catalyst, here we can say that this double bond is 1, 2, 3 tri substituted and this is di substituted. So tri substituted is keeping as such and di substituted getting reduced. So these are the important points to be considered in the case of the homogeneous hydrogenation of hydrocarbon. Okay, thank you.